of Technology in Stockholm. He's received many prizes, including the Best Research Award from Humboldt Foundation in 2008. And the title of his talk today is on the future stability of cosmological solutions to Einstein's equations with accelerated expansion.
So, first of all, can you hear me? Yes. Okay, so good. So, thank you very much. And so it's a great pleasure and an honor to be here speaking at the ICM. So I'd like to start by thanking the organizers for the invitation. So, in this talk, I want to discuss models of the universe which are consistent with observations. And in particular, I'm interested in the topic of future stability. But I'm also interested in the restrictions on the global topology that are imposed by observations. So, but let me start by describing the currently preferred standard models. So the standard starting point in cosmology is the so-called cosmological principle. So this is the assumption that the universe is spatially homogeneous and isotropic. And as a consequence of this assumption, Einstein's general theory of relativity is reduced to a choice of one of three spatial geometries and one scalar function of time, referred to as a scale factor. And the possible geometries are Euclidean, spherical, and hyperbolic. And currently, physicists seem to prefer the flat geometry. Right? So that's what I'm going to focus on in this case, right? So that you are actually in R3 spatial topology. Now, turning to the matter content, physicists, so it consists of three ingredients. So first there's the ordinary matter that we all sort of know and love, so like dust and radiation. Then there's something slightly more mysterious, referred to as dark matter, which is often modeled by dust. And then there's something even more mysterious called dark energy, which I will here simply equate with a positive cosmological constant, even though there are other versions. Right? So I will be more precise mathematically concerning what this means in what follows. Right? So normally, physicists would use so-called perfect fluids to model the matter. Here I will prefer the use of kinetic theory, or more specifically Vlasov matter, actually. But again, I will come back to this. Right? So that given these assumptions, the standard picture then is in cosmology is the following. So you would have a big bang, then you would have inflation, then there's a period of slow expansion, followed then by accelerated expansion driven by dark energy. And what I'm discussing here is sort of starting with a slow expansion, so after the so-called surface of last, or decoupling, and then on. Right? So this is what I'm interested in discussing. All right, so this is a nice picture arising from physics, but it does lead to a few questions, right? So the universe may or may not be almost spatially homogeneous and isotropic, but it's quite clear that it's not exactly spatially homogeneous and isotropic. Right? So this leads to the question of stability. Are these sorts of models stable to the future? Right? So this is one basic question. And another question you might ask, so the standard assumptions of spatial homogeneity and isotropy lead to a very strong restriction on possible global topologies of the universe. So then it's natural to ask, what are the restrictions imposed on the topology if you only assume every observer to consider the universe to be very close to a fixed standard model, as opposed to be exactly like a fixed standard model? Right? So these are the two questions I'm interested in this talk. Right? So, but before I proceed and discuss them in mathematical detail, let me discuss somewhat more detail what these standard models are. Right? So the cosmological principle, or the assumption of spatial homogeneity and isotropy, implies that the metric takes this form. Right? So here, t is just a standard coordinate on this open interval I. Sk is either hyperbolic, Euclidean, or spherical space, according as k is -1, 0, 1. G bar k is the standard metric on the corresponding space, and A is just a positive scalar function on this interval I. And I mean, in some situations, you might also be interested in taking quotients of SK by nice subgroups of the isometry group, right? But this is sort of the standard geometry, which is a consequence then of the cosmological principle. Now, turning to the matter content, as I said, it's usually described by perfect fluids. And so, in Einstein's theory, that's summarized in the stress energy tensor. And in the case of perfect fluids, and also this type of symmetry, the stress energy tensor can simply be summarized by two quantities. So two scalar functions of time, namely ρ, which is the energy density, and p, which is the pressure. Now, in order to predict the evolution of this solution, it's not enough. This is not enough. You usually impose some sort of equation of state relating the energy density and the pressure. And in cosmology, two very common choices are dust and radiation. And this corresponds to demanding, so dust, that's when the pressure is simply zero. And radiation, that corresponds to the pressure being a third times the energy density, right? So that's the sort of standard matter models that physicists use in these models of the universe. Now, in this talk, I'm more interested in something called velocity of matter. So the intuitive description of this type of matter is that you should imagine that you have a collection of particles, and let's say that they all have unit mass. And then, so then mathematically this would be, such a particle would be described by a future-directed unit timelike vector. And now, the main assumption in velocity of matter is that you neglect collisions. And the consequence of this is that the particles would travel along time-like geodesics. So they're sort of like pleasant particles. On the other hand, I mean, these particles, they will collectively generate a gravitational field, and thereby they will influence the geometry, and in the end, thereby the geodesics as well. Right? So it couples back to the geometry in this way. And then in order to describe this collection of particles, you use something called a distribution function. And this should be thought of as describing the average properties of an ensemble of collections of particles. So that's sort of the intuitive description. But so this is the main matter model in this talk. So let me describe the mathematical details of this. Right? So the essential mathematical structures here is, first of all, something called the mass shell. Right? So this is a set of future-directed unit timelike vectors. So it's the elements of the tangent space whose scalar product with themselves is -1, and also point in the right direction, the future direction. So this you should think of as the space of states of particles. Right? Then you have the distribution function defined on this space of states. And then, in order to connect all of this with Einstein's general theory of relativity, I need to explain to you how to construct a stress energy tensor out of the distribution function. And the prescription is the following, right? So it's this formula here. So the components of the stress energy tensor, T alpha beta, at some spacetime point psi, is given by this integral. Okay, so you're integrating, first of all, over a set p psi. So what's p psi? Well, it's the set of future-directed unit timelike vectors based at psi. Right? So in Minkowski space, you take the origin in Minkowski space, this is simply the hyperboloid, right? The standard hyperboloid. And this is a subset now of the tangent space. So you're integrating over that set. And what is the integrand? Well, first of all, it's you take the distribution function, which restricts, of course, to a function on p psi. And then you take this little p alpha, little p beta. So little p is just an element of p psi, right? And then p alpha, well, you lower the indices with a metric. So this f p alpha p beta, this is a perfectly good function on this set p psi. And now you need a volume form in order to integrate this quantity. And the volume form, I denoted mu p psi, and it's gotten the following way. So the Lorentz metric G induces actually a Riemannian metric on p psi, and this Riemannian metric induces a volume form, and mu p psi is that volume form. Okay, and then the matter you can't specify freely. It also has to satisfy an equation, and I mean, so as a consequence of this assumption that you neglect collisions, the relevant equation is this one, so LF equals 0. So the geodesic flow defines a natural vector field on the mass shell, and I've denoted it by L, and the equation is LF equals 0. So this is just a statement that F is constant along unit time like geodesics. Okay, so that's the loss of matter, and so to summarize, the relevant equations are the following. So it's, first you have Einstein's equations, so it's capital G plus lambda little g equals t. So here, capital G is the Einstein tensor, that is to say the Ricci tensor minus a half times the scalar curvature times symmetric. Capital lambda is the positive cosmological constant representing this dark energy. And then on the right-hand side, you have the stress energy tensor I wrote down on the previous transparency. And then you have the loss equation. So this is now an equation for the metric G and the distribution function F, and it's a system then of geometric nonlinear integral partial differential equations. Okay, so now so before I proceed to a statement of stability, let me discuss in somewhat greater detail the background solutions I'm interested in proving stability of. And so as I said, the currently preferred models are spatially homogeneous, isotropic, and spatially flat, and then the metric takes this form, so minus the t squared plus a squared of t g bar. Here, a is the scalar function of time, and g bar is the Euclidean metric. Right? So that's the metric. And now, in this, if you make this sort of symmetry assumption, then actually the velocity of matter also takes perfect fluid form. Right? So it can also be summarized by an energy density and a pressure. On the other hand, it's not going to, there's not going to be some simple equation at stake. On the other hand, you can actually write down the energy density and the pressure in terms of the initial datum for the distribution function and the scale factor. So in these formulas here, so rho Vlasov and P Vlasov, this is the energy density and the pressure in this case. It turns out, so F bar, this is like a symmetry reduced version of the initial datum for the distribution function, and A is of course the scale factor of the model. So here you get an energy density and a pressure, just like in the case of perfect fluids. So now it's of interest to sort of compare this. How does this compare with the dust and radiation that physicists normally use in their models? So then it turns out that, well, if you just take the initial datum for the distribution function to be the Dirac delta centered at the origin, well then actually the pressure just vanishes. But the energy density does not. Right? So in this case, dust is a very special case of this situation where you just put the distribution function to be a Dirac delta function. Now, radiation, well that's also in some respects a special case. So if you take massless particles instead of massive particles, then this 1 plus absolute value q squared turns into absolute value q squared. And then it turns out, then if you look at this, you see that the pressure is simply a third times the energy density. So you actually recover this radiation. That's actually another special case. Right? I'm here interested in smooth distribution functions, but you can actually approximate very well both dust and radiation, well, for limited periods of time with smooth distribution functions if you choose this sort of initial data. So in the center you have something approximating a Dirac delta function, and then you have something far away approximating the radiation. So if F has support very far away from the origin, this is essentially radiation as well. And to the future there is no problem in approximating dust. But in some sense I would say, I prefer loss of matter to dust and radiation for the simple reason that, the reason why physicists normally put in dust and radiation is that, so they want behavior like radiation close to the singularity and dust in the expanding direction. Now, loss of matter actually dust is naturally, so it will behave like radiation close to the singularity and it will behave like dust in the expanding direction. Right? So in that sense, from my point of view, this is a more natural model, which I personally prefer, right? So that's why I'm working on that. Okay, so when we're going to discuss this issue of topology, then it's useful to have a feeling for the causal structure of the standard models. And in order to have something with which to compare, it's quite natural to start by looking at Minkowski space, right? So let's ask the following question. Let's take an observer in Minkowski space, which is just sitting at the origin. So this corresponds to the curve gamma t equals t comma 0, 0, 0, right? And then you can ask the question, how much of the t equals 0 hypersurface does this observer see? And I plotted the result here for t equals 1/2, 1 and 2, and as you can see, the pictures are not very exciting. Right? They look pretty similar. The only difference is that the scale, right, of the axes. So the point is, so I will refer to this as a non-silent causality for the simple reason that regardless of how far away from the origin you are in the t equals 0 hypersurface, you can always communicate with gamma. You can send information to gamma. Right? So this is the type of causality you have in the Minkowski space. Now let's look instead at the Sitter space. So this is the sort of simplest solution with a positive cosmological constant. So a part of the Sitter space can be written like this. So it's just minus dt squared plus e raised to 2t g bar. G bar is just a flat Euclidean metric on R3. And, okay, this is a specific value of the cosmological constant. So if you now ask exactly the same question, then for t equals 1/2, the picture looks very similar, right? The observer sees something which is quite similar to sort of the light coming in the Minkowski space. But for large t, the picture is very, very different. So the fact is that if you let t go to infinity, the observer will not see more of the t equals 0 hypersurface than a ball of radius 1. So this I will refer to as a silent causality, because if you are outside the ball of radius 1, you cannot communicate with gamma. You can never send any information to gamma. Right? And it's important to realize that this is the type of causality which is relevant for the standard models of the universe today. Right? You sort of lose the ability to communicate. Right? Okay, so now so in order to formulate the stability result, I need to first of all justify that there is an initial volume problem for these equations, and also to tell you how to measure the distance between initial data sets. So let me start first by briefly discussing this topic of formulating an initial value problem for the Einstein-Glasov system. Right? So let's first assume that you actually have a solution to the Einstein-Glasov system, right? So NGF. And you should think of the equation for the metric to be like a wave equation for the metric component. So as a natural initial hypersurface on which to specify initial data, well, for the standard wave equation, it's a constant t hypersurface. More geometrically, that's a space-like hypersurface in Minkowski space. So now let's take a space-like hypersurface in the this Lorentz manifold Ng. Right? So let's look at a space-like hypersurface sigma in the solution. Okay, so what should the initial data on this hypersurface be? Well, so if you think of the equation for the metric components like roughly a wave equation, then okay, so you want to specify the initial datum for the metric components and the first derivatives. But this is a geometric problem, and as a consequence, it's natural to take the induced metric and second fundamental form, which roughly speaking correspond to this sort of information. Now for the distribution function, the situation is slightly easier. It's a first order equation, so you just take the induced distribution function on the initial hypersurface. So this will be defined on the tangent space of sigma. Okay, right, but now, and unfortunately, these quantities are then not freely specifiable. They have to satisfy, they're actually related by so-called constraint equations, but I'm going to omit them here in this discussion. So now I've been going in the wrong direction. You start with the solution, and then you get these quantities, sigma, g bar, k bar, and f bar. Right? What you want to do is you want to go in the other direction, and it turns out to be possible. So if you start with a manifold sigma, a Riemannian metric g bar, symmetric covariant 2 tensor field k bar, and this quantity f bar satisfying the constraint equations, you can actually construct a development associated with this data. In fact, there is a so-called maximal Cauchy development associated with this data. So there is such a thing as an initial value problem. Now, in order to sort of state stability, I also need to tell you what does it mean for two initial data sets to be close. How do you measure the distance between initial data sets? Well, I'm mainly going to be interested, or I'm only going to be interested, in fact, in the case of compact hypersurfaces sigma. And then you can use standard sublove spaces for g bar and k bar, so that I'm not going to discuss. In the case of the distribution function, it's a little bit more complicated. It's defined on the tangent space. Let me just flash the norm. So this roughly speaking like the Sobolev space norm. It's just that you need some weights in the tangential directions, right? So this is the sort of norm you would use to measure the distance between distribution functions. Okay, so let me say briefly a few words about previous results. So, in the case of exponential expansion, right? So, the first result was obtained by Helmut Friedrich in 1986. So he proved stability of 3 + 1 dimensional de Sitter space. And then he later on proved stability also for other matter models such as Maxwell and Yang-Mills. Later on, Michael Anderson continued in the same vein, proving stability of de Sitter space in even space-time dimensions. So these are very nice and geometric results, and they were proven by sort of conformal techniques. And you get very, very precise asymptotics, but there's a slight problem. They don't seem to be that robust. They're very dependent on the matter models having strong conformal invariance properties. So they cannot be expected to hold, for instance, for Vlasov matter or other types of matter that I'm interested in here. So then, for that reason, I wrote a paper in 2008 where I considered the Einstein nonlinear scalar field setting, and the main goal there was to develop methods that can be applied in more general settings. Right? And later on, there have been several results sort of using where these methods then have played an important role. So, for instance, with the Einstein nonlinear scalar field setting, with the Maxwell field, various types of potentials. There are also results in the Einstein-Euler setting by Jared Speck and Igor Ogniansky. Right? So several results on this. And also what I'm going to discuss today is in the Einstein-Vlasov setting, is using these sorts of methods in this paper from 2008. So I mean, of course, if you add these different types of matter models, there are additional complications, right? But there are some ideas from this paper that turned out to be useful. Okay, right, so now I can actually state the stability result. And before I do that, I should specify the initial data, the relevant initial data. So let's just take initial data. So in this case, G bar background, K bar background, F bar background, corresponding to an expanding solution to the Einstein-Vlasov equation with positive cosmological constant. Now I want to make two. So this is essentially all the data which yield expanding solutions. Then I'm making two technical restrictions here. I'm excluding so-called Bianchi 9 and Potocki Sachs. I'm assuming that there's a co-compact subgroup of the isometry group so that you get compact quotient. This is somewhat technical assumption, so I would prefer not to go into this in detail unless you insist. So then taking these, okay, so these are the initial data that I'm interested in. Let me just point out that, so there are solutions to the Einstein-Vlasov system which, first of all, are consistent with observations, and second of all, induce initial data of the type that they fall into this category. Right? So you just take G to be R3, you take G bar background, K bar background to be some suitable multiples of the Euclidean metric, and then you make some informed choice of this F bar background. Right? So, I mean, proving stability of models of the universe which are consistent with observations, that's a very, very special case of what I'm discussing here. I want to point that out. I should also point out that within these classes of initial data, you also find initial data with a very large degree of anisotropy, right? So it's not like I'm staying close to the isotropic case. I'm insisting on spatial homogeneity, but I'm not insisting on spatial anisotropy. So if you take initial data of this type, what are the conclusions? Well, then there is an epsilon, so that if you take initial data to the Einstein-Vlasov system, which are epsilon close in this specific sense, right? So G bar and K bar are epsilon close in H5 and H4 respectively, and then the F bar is epsilon close in this H4, this weighted space I mentioned earlier. Well then, first of all, the maximal Cauchy development is future Cauchy geodesically complete. Right? So this is sort of the geometric statement of the fact that the solution is global to the future, right? So if you take a freely falling test particle that corresponds to a time-like geodesic, and this freely falling test particle is not going to exit the space-time in finite time. This is still rather soft. You would like to know a little bit more about the asymptotics. In fact, you could write down pages and pages of estimates here. I'm going to spare you the details. But suffice it to say that the solution to an observer becomes asymptotically de Sitter-like. So this very simple model solution I explained to you earlier, described to you earlier, I mean, all the observers will consider the universe to become de Sitter-like to the future. So in particular, even if I start with a solution which is very anisotropic, even the background solution is very anisotropic, then all these solutions will appear isotropic in the limit. So in this case, the cosmic no-error conjecture holds. Okay, so let me now move on to the issue of the shape of the universe, right? So okay, so what's the shape of the universe, right? So that's the question you might want to ask. And more particularly, what are the limitations on the global topology imposed by the constraint that what we see to the past is close to one of the standard models? Or to be a little bit more precise, let's assume now that, okay, the observational data indicate that to our past, the universe is well approximated by one of the standard models that I explained before. But now, okay, spatially flat, right, and with R3 spatial topology. And that physicists are telling us that's the case, right? And if you interpret data in this model, we only have information concerning the universe to the future of some t equals t0 hypersurface, which is not the Big Bang. So what you should think of here physically is that, well, you look back out into the universe, and usually the way to collect information is by electromagnetic radiation. Right? And then there's a moment of decoupling where matter and radiation decouples, right? And you can't really see beyond that, right? So you should think of, and anyway, the models that I'm discussing are not relevant beyond that point, right? So you should think of, you see back to this point where matter and radiation decouples, and you can have information what happens after that. Right? So, and this T0, you should think of that as corresponding to this decoupling. Right? And then let's assume there's a Big Bang. Well, physicists are telling us that this is the case, right? So, and then the final assumption is rather philosophical in nature, and this is the common in cosmology, right, that you make some sort of philosophical assumption in the form of the cosmological principle. So here, I'm going to assume that analogous statements apply to all observers in the universe with the same T0. Right? So, otherwise, of course, you have lots of freedom. But let's make this assumption as well. Right? And then the crucial question is, what conclusions are you allowed to draw concerning the global spatial topology of the universe? And I would then here like to argue no conclusions at all. Okay, so that's what I'd like to argue. And it's a little bit interesting here to sort of to compare this with the standard assumptions of exact spatial homogeneity and isotopy. So normally you would assume that the universe to appear exactly like one fixed standard models to all observers, and then of course you get very strong restrictions. Right? But here, if you just let go of this assumption that it appears exactly spatially homogeneous and isotropic, then all of a sudden everything goes, anything goes. Okay, so this statement is still a little bit vague. So let me take one step more in direction towards a mathematical statement. So what do I really mean by this statement I made? So let's assume now that you give me the following data. So first of all, you give me a standard model. So this is spatially flat R3 spatial topology. And this is characterized by an existence interval I, there's a scale factor A, there are various matter quantities. So that you give this to me. And this is how the universe is supposed to appear to observers. Right? Then you also give to me a time t0 in the existence interval of this standard model. And this point represents, so this represents the point to the future which you want to approximate the solution. And you should physically think of this as representing decoupling. Right? So I want to approximate the solution after decoupling. Then you also get to specify to me a natural number And if you specify L, then I'm going to measure the distance of the solution to the background solution with respect to the CL norm. I'm still a little bit vague because there are various weights you have to use also. So here I could still become a little bit more precise, right? But I'm not going to go through the details, right? And then you also get to specify an epsilon, and this is going to characterize the distance to the background solution. And finally, you get to specify a closed three-manifold. Just give me any smooth closed three-manifold system, right? So this is the data you provide to me. And if you do that, what I will give you in return then, what I'm going to give you in return is the following. So I'm going to give you a solution to the Einstein-Lasso system, so MGF. And this solution will have the following properties. First of all, it's going to be the maximal Cauchy development of some initial data. It's going to be future causally geodesically complete. Right? So in this sense, it's geometrically global to the future. Right? In this solution, there will be a so-called Cauchy hypersurface S bar, which is diffeomorphic to sigma. So what is a Cauchy hypersurface? Well, this is a hypersurface which is intersected exactly once by every extendable timeline curve. And in this case, so these maximal Cauchy developments, they're always globally hyperbolic. And this means that the topology will always be R cross a Cauchy hypersurface. Right? So in this case, the topology of the universe will be R cross sigma. Right? So in this sense, the topology will be the one you specified to me in the previous transparency. And now, physically, you should think of this S bar as corresponding to decoupling. Right? So when matter and radiation decouples. And, or to the point t equals t0 that you specified to me previously. And now comes the difficult part, right? So now you need to compare this solution that I've constructed with the background solution. Right? So how is that going to happen? So the problem here is that the solution MGF and the background solution, they have different topologies and so on and so forth. Right? But the main point here is that you only want to compare regions that can actually be seen by observers. So what are the regions that can be seen by observers here? Okay, so let's then pick an observer. What is an observer in the first place? Well, it's a causal curve. So it's a curve gamma such that the scalar product of its tangent vector with itself is less than or equal to 0. Right? Okay, so you pick an observer, any observer in the solution MGF. And now you ask the question, what does it see? Well, the largest region of the space-time this observer can have any information whatsoever is its causal past. And that's denoted J minus of gamma. Right? So it's this, right? So this is a set of points which can be connected to gamma by future directed time causal curves. Right? So that's the largest set concerning which gamma can have information. And then I was also assuming that the observer can also only have information concerning the universe to the future of this t equals t0 hypersurface, which then corresponded to S bar, right? So then, actually, what you're interested in, okay, if you take this J plus of S bar, these are all the points to the future of this hypersurface S bar. So by hypothesis, the largest set concerning which the observer gamma can have any information whatsoever is this J minus of gamma intersected J plus of S bar. And so that's the largest set. And this is the only set you actually want to compare with the background solution, right? Because this is the only set concerning which gamma can have any information. Okay, and then the point is here that if you take just any causal curve gamma, right, it turns out there is a neighborhood U of this set, and there's also a diffeomorphism from a solid cylinder in the background solution. So the solid cylinder is over here, so T0 infinity times B R 0, right? So there's a diffeomorphism from this, well, a neighborhood of the solid cylinder to U. And then if you pull back the solution MGF to the background solution using this diffeomorphism, and you compute the difference between the background solution and this pullback solution, the error will be epsilon small in the CL norm that I prescribe to you. So in this sense, the observer cannot tell the difference between this solution, MGF, and the standard background solution that you gave to me at the beginning. Right. Then, moreover, in this spacetime, all time-like geodesics are past incomplete. So a freely falling observer, a test particle, is just going to, well, exit the spacetime in finite time. So something bad happens to the future. I can't say anything in detail concerning what happens. You expect this to be a Big Bang singularity, right? And finally, and this is quite important, I mean, this is not just any very special construction that I've come up with. The solution is actually stable with all of these properties. So if you take initial data corresponding to a solution of this type, you can perturb them, and you will get a solution with all the same properties. Right? So this is not just a very special solution, this is a robust construction. Right? Okay, so the conclusion then is that any closed three-manifold here will do. Right? So you can't really tell anything about the spatial topology. If the standard models are the currently preferred one, you can't say anything about the spatial topology. Okay, so this was a bit brief. If you want to know more, there's a book, and you can actually browse it in the Oxford University Press then, if you want to. But this was all I wanted to say, so let me thank you for your attention.
Other questions?
Can you describe briefly on what ideas is based this stability theory?
Okay.
Maybe repeat the question.
Okay, so Professor Chrysodoul wanted to know on what ideas the stability theorem was based, right? So, I mean, well, okay, so it's based. I mean, it's based on energy methods, right? I mean, so you want to. I mean, it's due to the fact that you have the Glossop equation. So after sort of making a so first you have to make a suitable gauge choice, right? So in the equations, and then it turns out you also. I mean, okay, so it's based on these sorts of gauge source functions, right? And you also have to add certain sort of corrections to the equations, but then you get a system of nonlinear wave equations coupled to the Glossop equation, and then of course it's sort of an integral partial differential equation, right? And then okay, so then it's a matter of you want. I mean, so it's a big bootstrap argument with energy methods and so on and so forth. In that respect, it's.
But the positive cosmological constant, the growth.
Okay. So the positive cosmological constant plays a very important role, of course. Right? So I mean, so the thing is that the positive cosmological constant gives you this exponential expansion, right? So I mean, if you sort of throw away the terms that are quadratic in things that vanish on the background, let's say, right? I mean, then you get sort of wave equations, sort of linear type wave equations where you have even exponential decay, if you make the right choice of equations, right? Then of course you have to deal with the Vlasov matter as well. That's slightly a technical issue somehow, but essentially, I mean, if the linearized system is very nice, right? The main problem is really that it's slightly messy to estimate the error terms, because you have very different growth in different components somehow, and to do that in a systematic way is slightly messy, right? So that's where it becomes a bit technical somehow.
More questions? Okay, so if not, let's thank the speaker again. Okay, here is the little gift from the local organizing committee.